ones right now. Okay. All right. Okay, give me a second. Okay. No. Let's do this. I think this is 5.2, right? The Fundamental Theorem of Calculus. So there's two parts to the Fundamental Theorem of Calculus. This is part... Well, what's interesting is, so I always call this part 1. Depending on what book you're reading, they sometimes have them flip-flopped. So there's nothing special about the different parts. This one is the more useful one in general. So I like doing this one first. So the plan is we'll talk about the fundamental theorem, and then we'll talk about why it's true, and then we'll prove it at the beginning of next class so that your brains are fresh when we prove it. But the idea is actually not very complicated. Okay, so here we go. Are you guys ready? Okay, so suppose f is continuous on the closed interval from a to b. And capital F of x is an antiderivative of little f of x. Do we know how to find antiderivatives? Okay, good. Then the integral from a to b of f of x dx is equal to capital F, which is what? The antiderivative, evaluated at b, minus capital F, which is antiderivative, evaluated at a. What? That is crazy talk. What are you talking about? So we have on the left side the area under the curve, the function, f of x, from a to b. And then we have on the right side something completely light years away from having anything to do with the area, the antiderivative. The antiderivative is that stuff that we did the other day, and that has nothing to do, right? The two do not have anything to do. Well, in reality, they do have something to do. What? Okay, all right, so let's talk about this. So see, it is not actually very complicated. It's based off of what we talked about a little while ago. So, let's get a good understanding here. So let's say, for example, so take your function here. So let's say this is f of x, and think of this as representing velocity. So just like the example we just saw, yeah? So the function represents velocity, right? And you have here a, you have here b, and this right here, the area underneath the curve, is what we're trying to find. This area under the curve is all that stuff right there. Okay, so the integral from a to b of f of x dx is the area under the curve. So far, so good? Okay, now, but if you instead of narrowing your focus and just thinking about area, if you instead think of the function as representing velocity, as we just talked about, this same area right here, all this that I had colored in orange and now is green, what does that represent in the context of velocity and distance and all that jazz? It's the displacement, right? Displacement slash distance, right? Not divided by, but you know what I mean, right? So you have to be just a little bit careful because distance, everything is counted as positive. And displacement is the distance, the net distance, right? So, okay. But anyways, okay, so now, so we have that down. Now, let's go back to this function, right? The antiderivative of the velocity function, okay, so this is key. The antiderivative of the velocity function is what? Is position, right? Is the position function. You guys agree with that? We did that when we talked about antiderivatives, right? You have the position function, you get its derivative, you get the velocity. Get the derivative of velocity, you get acceleration, right? And so then you can go back, right? So if you have acceleration, you get the antiderivative, you get velocity. Get the antiderivative of velocity, you get the position, right? Okay, so this is the key thing here. So here in this case, we're calling it capital F of x, right? So far, so good? Okay, so if you got the antiderivative, that means you have the position function, right? Okay, so if you have the position function, then how do you find the displacement? So if capital F of x is the position function, the displacement so remember the displacement, what does that represent? That's just the distance you are from, the distance you've traveled, the net distance, right? So if, for example, you know, what is that right there? Yes, but in the context of all this stuff, velocity, displacement, this is the final position, right? What is this? That's the starting position. If you subtract the two, what do you get? That's the displacement. That is nothing more than the displacement, exactly. So all it takes is that mental switch. Instead of thinking of it as area, think of it as a rate of change, and then the connection is clear, right? Because if the function itself is velocity, then the area under the curve is just the displacement. But if we have velocity, we already know how to find the displacement, right? It's just the antiderivative, and at that point, just find the difference of the two, and then that's it, right? So what this means, though, is that instead of doing all that crazy stuff that we were doing, right? So like here, if I, for example, okay, so compare the integral of, I don't know, what was one of the first ones that we did? I don't know, didn't we do something like, I don't know, do you guys remember? What's the very first one we did? 0 to 5? Of what? What was it? No. Give me the very first integral we did. Whatever it was. Or the second. It doesn't matter. Something we've done before. One integral we've evaluated before in our lives. No. Not today. No, I mean, like on, what is it? Wednesday? Or
From 1 to 4? 1 to 4, 2x plus 10.
of 2x plus what? 1. Okay, there we go. All right. This we did crazy sum stuff, right? And then what did we get? 18? Okay. All right, so this one actually wasn't that bad, right? Ah, what happened? Okay. All right, now, using the Fundamental Theorem of Calculus, let's do the same one. Okay, so we're going to compare it. So we're going to do exactly the same one. Okay, so this is going to be complete overkill because we're going to use all the properties just for practice and for fun. Typically, you would do this in one step, but let's do it using the properties. So here we're going to break this up into the integral from 1 to 4 of 2x dx plus the integral from 1 to 4 of 1 dx. So that was the property that you can break up the sum of two functions into separate integrals. Yes? Okay, then what else can I do? What other property? I can factor out the 2, right? So take out the 2. Not factor out the 2, just take out the 2. So then I have 2 times the integral from 1 to 4 of x dx plus the integral from 1 to 4 of 1 dx. Okay, so are we okay with that? And as you'll see, as you get more practice, you won't do this extra step. You'll just do it in one, but that's fine. Okay, so then what is this equal to? So what does the Fundamental Theorem of Calculus tell me to do? Take the function, get its antiderivative, right? So what's the antiderivative of x? Remember the power rule for antiderivatives? It would be x squared over 2, right? Okay. And then, so this is the way that you normally write it. So I'll give you the notation. So you put a vertical line like this, and then you put the same limits of integration that you had earlier, 1 and 4. And we'll plug them in on the next step. Okay? So this just means you're going to plug these numbers in, 4 and 1, and you're going to plug them in top first and then minus the bottom, right? So that it matches up, because it's f of b minus f of a, right? So it's always top minus bottom. Does that make sense? Okay, now plus, what's the, so then again, the antiderivative of, in this case, 1, what's the antiderivative of 1? X, right? And then again, evaluated from 1 to 4. Okay. All right, so now what is this equal to? This is 2 times, this is what, 4 squared over 2 minus 1 squared over 2, right? So we plug in the top minus plug in the bottom plus 4 minus 1, right? And then what is that? So in the parentheses here, so we're kind of running out of room here, but it's 4 squared is 16 over 2 is 8 minus, well, that's just a half, right? But then times 2, that's going to be 16 minus 1, so 15 plus 3, which is 18. Look at that. Isn't that exactly what we got last time? Okay, now that looked long, but after we get the hang of it, we can, all these kind of properties steps, we just do that in one and then be done with it. That one wasn't that bad, but the next one we did, do you guys remember? So let's see. So we also did, what's another integral we did? The next one after that, an ugly one, right? We did a quadratic, didn't we? X squared minus x plus 1. From where? 2 to 4, okay. So we did crazy stuff again. This one was worse. This one took us probably an hour to work it out, right? And then what did we end up with? Probably some fraction, right? 44 over 3. Okay, crazy stuff. 1 hour later, we get 44 thirds, right? Okay, then using the Fundamental Theorem of Calculus, okay, so let's get the antiderivative. So what's the antiderivative of, so we'll do it all in one step this time. So what's the antiderivative of x squared? X cubed over 3, yep. Minus, what's the antiderivative of x? X squared over 2 plus the antiderivative of 1, bless you, x. Okay, and then I'm going to evaluate here from 2 to 4. So far, so good? So then what's the next step? Is to plug in top minus bottom, right? So plug in 4 minus plug in 2, right? So I'm going to have 4 cubed over 3 minus 4 squared over 2 plus 4. So that's the top. Minus plug in the bottom. So same thing, this case 2 cubed over 3 minus 2 squared over 2 plus 2. Does that make sense? Okay. So let's simplify this a little bit. So 4 cubed, what is that? $64, right? Over 3, okay. Minus, let's see, 4 squared is 16, over 2 is 8, plus 4. Then the main thing, so the biggest mistake I see is with signs, obviously. Notice we're subtracting, and then you're adding, subtracting other stuff. So just make sure you're extra careful. So what is this going to be? This is going to be minus 8 thirds, right? And then 2 squared is 4, divided by 2 is 2. So minus 2, right? And then plus 2. Just making sure. I warned you that time, but I won't always warn you. So plus and then minus, right? Okay, all right. All right, and so then what does this equal to? Well, let's see. So plus 2 minus 2, that's 0, right? Minus 8 plus 4, that's negative 4, right? And then, okay. How many thirds is this? 56 thirds. So if I multiply this top and bottom by 3, I get 12 thirds, right? So what is that? 44 thirds. Look at that. Exactly the same as what we got earlier, right? That's pretty cool. So how long did that take us? That second one? A couple minutes maybe, right? Compared to 1 hour, that's quite the bump in productivity there. So any questions with that one? So that's pretty awesome, huh? We're only getting started with the awesomeness. What about, for example, something that you can't do with the sum? So like let's say the integral from 0 to pi of sine of x. let's say. Could we have done this using the sum formula stuff? No, right? Because there's no way for us to do an infinite sum of sines. But using the fundamental theorem, is this easy or difficult? Easy. It's like I don't know. What is it? It's like eating cake. Easy. All right, so what do I do? Which is? Minus cosine x. Well, notice you don't put the plus c. So notice we haven't been putting the plus c. How come? It wouldn't change anything. You're correct. But, well, let's put the plus c. Let's see what happens. You guys see what's going to happen? Well, let's just leave it in. It'll be fine. All right, so what do I have? Minus cosine of pi plus c, right? Minus cosine of 0 plus c. What happens with the c's? They cancel out, right? So you have plus c, but then you have minus c, so then that's why you never write it, because it's just going to cancel out anyway, so you can write it if you feel like it, but you don't have to. When it's a definite integral.
What does that mean?
What?
A definite integral.
Well, a couple lectures back, we had indefinite integrals. Maybe more than a couple, maybe 3 lectures. When we did antiderivatives, you guys remember? So, definite versus indefinite integral. Okay, so definite is, looks like that, right? This is, find the area under f of x from a to b. Yes? That's what we've been doing. Indefinite integral looks like this. No a and b. So what does this mean? What do I do here? Find the general antiderivative of f. Right? So, actually, now that I think about it, I don't know if we mentioned the indefinite integral back then. Did we? No. Yeah, I think maybe we didn't, because I didn't want to confuse. Yeah. So this is, so all the integrals we've been doing are definite integrals, because you're finding the area under the curve from this point to this point. If you have an integral that doesn't have limits of integration, that just means find the antiderivative, the general antiderivative of the function. And so then, so like for example, if you want to, what's the integral of, I might as well. Sine of x dx. What is that? That's minus cosine x plus c. And then that's it. You're done. There's no b minus a business. It's just the antiderivative, and then you're done. Does that make sense? So then what did we end up getting for this? This is minus what? Cosine of pi is -1. And then minus 1. So what is that? 2. Good. Not 0, right? 2. So notice this is sine, right? Looks like this. And what did we just find? We found this area right here is 2, right? Cool beans? Okay.